One of the problems that we still face is it will turn out that we care quite a bit about finding the definiteness of a real symmetric matrix. But the only way we really know how to do it is by looking at the eigenvalues of that matrix. And as we've seen, calculating eigenvalues can be quite difficult. So it would be nice if there were a more efficient method for determining definiteness. And Cholesky factorizations is one way to do this. So I want to start, before we talk about Cholesky factorizations, talking about another type of factorizations which will lead us to Cholesky factorizations. And that's the concept of an LDL transpose factorization. So by definition, an LDL transpose factorization is an equation of the form S equals L times D times L transpose. Now in this factorization, L is an n by n real lower unitriangular matrix. And that term uni and unitriangular means that there are ones on the diagonal of L. D in this situation is an n by n real diagonal matrix. And of course, L transpose is the transpose of L. Now, once I have an equation that looks like this, if we look at the transpose of S, that's the same as the transpose of L times D times L transpose. And if we use the order reversing property, that's the same thing as L transpose transpose times D transpose times L transpose. But L transpose transpose is L, and since D is a diagonal matrix, D transpose is D. So this ends up just producing S. So the point is, once I know that S is equal to L times D times L transpose here, that forces S to be an n by n real symmetric matrix. So LDL transpose is something that only real symmetric matrices can have here. So let's just look at our first example. Here I have a real symmetric matrix S on the left here, factored as L times D times L transpose. So as we can see, L here is a lower unitriangular matrix. That means it's a lower triangular matrix with ones on the diagonal. D here is a real diagonal matrix, so the only places where there aren't zeros in D are on the diagonal. And then L transpose, of course, is the transpose of L. And once we have this factorization, of course, that forces S here to be real symmetric, which if we look at it, of course it is. Now, what's the point of studying LDL transpose? Well, if S is real symmetric, that means it defines a quadratic form. The quadratic form is the inner product of the input vector x with L times D times L transpose times x. And we've seen things that look like this before. When I look at this, I kind of see an unbalanced inner product. So I like to move the L to the other side using the adjoint property of inner products. And that gives me L transpose x, inner product with D times L transpose x. So now I can change variables, much like we did when we completed the square using the spectral theorem, except this is a totally different factorization. This is now, if I set y equal to L transpose x, I'm now looking at the inner product of y with D times y. And the nice thing about this expression is that I can now write this as a linear combination of squares, where the coefficients are the diagonal entries of D, and the squares are the coordinates of y, which is L transpose times x. So this is d1 times y1 squared plus d2 times y2 squared plus dn times yn squared, where these d's are coming from the diagonal of d, and the y's are the coordinates of L transpose times x. And so, of course, once we have this expression, again, much like in completing the square, except this is now totally different, what we see is that it's the diagonal entries of D that control the definiteness of this quadratic form. So all we have to do is look at the signs of the diagonal entries of D, and that automatically tells us what the definiteness of the quadratic form is. Let's look at an example. Here I have a real symmetric matrix S factored as L times D times L transpose. If I look at the quadratic form defined by this real symmetric matrix S, I take advantage of the calculation we just did and realize that this is d1 times y1 squared plus d2 times y2 squared plus d3 times y3 squared. What are those specific entries? Well, d1 here should be the first diagonal entry of D, which is 3. y1 should be the first coordinate of L transpose times the input vector x, if I multiplied L transpose here by x1, x2, x3, the first coordinate would be 1 times x1 minus 3 times x2 plus 2 times x3. So that's my y1 here. So my first term is 3 times y1 squared. The next term should be d2, which is the second diagonal entry of d. That's negative 7, multiplied by y2 squared. And y2 squared, or y2 would be, let's see, if I look at the second row of L transpose, that should be x2 plus 5x3 quantity squared now. The last term here should be the third diagonal entry of d, which is equal to 5, multiplied by y3 squared. Well, what is y3 squared, or y3 here, equal to? It should just be equal to x3. So now I get x3 squared. So I have a nice way of presenting this quadratic form as a linear combination of squares. And what I see in my coefficients is a mixture of positive and negative numbers. So that tells me that the definiteness of this quadratic form is indefinite. Two of the diagonal entries of d, d1 and d3, are positive, that's 3 and 5, and the middle one, d2, is negative. So sometimes this quadratic form is positive, sometimes it's negative, which means this is an indefinite quadratic form. So if I have L times D times L transpose, I can quickly infer the definiteness by looking at the diagonal entries of D, and the reason that I can do this is because I have this nice way of writing my quadratic form. So this looks a lot like what we did when we completed the square, but the difference is that completing the square required the spectral theorem, which required that we calculate the eigenvalues of S. Here, we're not doing anything with eigenvalues, we just have a nice presentation of S.